It is the 8th of September 2025, approximately 11:37 a.m. Moving on to exercises involving dihedral groups. Camera appears to be working well. So, exercise 1 here, compute the order of each of the elements in the following groups. And then we're given these dihedral groups, as is the necessity of this chapter right here. So D6, D sub 6, D sub 8, and D sub 10. Quick camera check. Camera's good. Now, intuitively speaking, in D sub 2n, we have that equals the group generated by RS, such that R to the n is equal to S squared, which is equal to 1. RS is equal to SR to the negative 1. The subgroup generated by R is cyclic of order n, and each reflection, SR to the k, has order 2. Thus, identities have order 1 rotations, have order dividing n, and reflections have order 2. The only subtlety lies in identifying which powers R to the k have smaller order. So let's get into that a bit more rigorously here. Here, I check that. Yep. Let's see if mine works better. Kind of. More of a grid to it. Alright. So, looking at this more rigorously for the proof, step 1, let's look at the elements of, this is for A, of D sub 6. Here, n equals 3. So D sub 6 is equal to the set containing 1 R, R squared, S, SR, SR squared. The order of 1 is equal to 1. Right, so the order of R is equal to 3. The order of R squared is also equal to 3. Now, the order of S is equal to the order of SR, which is equal to the order of SR squared, which is equal to 2. Think about that. It's the first one. Okay. Now let's move on to part B. elements of d sub 8. Here, n is equal to 4. So, what are the elements of d8? Well, those are 1, r, r squared, r to the power 3, s, sr, sr to the second, and finally sr to the third. Now, the order of 1 is equal to 1. The order of r is equal to 4. The order of r squared is equal to 2. The order of r cubed is equal to 4. The order of s is equal to the order of sr, which is equal to the order of sr cubed, squared, which is equal to the order of sr cubed, which is equal to 2. Now, elements of d sub 10. Here, n equals 5. That's a prime. So, subgroup, well, the group generated by R is cyclic. Of order 5. And each non-trivial r to the k, such that k is equal to 1 all the way up to 4, has order 5. Each reflection has order 2. So the order of 1 is 1. The order of r is equal to the order of r squared, which is equal to the order of r cubed, which is equal to the order of r to the 4, which is equal to 5. The order of s is equal to the order of sr, which is equal to the order of sr squared, which is equal to the order of sr cubed, which is equal to the order of sr to 4, which is equal to 2. Thus, in each case, the rotation subgroup has the expected orders dividing n and all reflections square to 1. So it completes exercise 1 of 1.2. On to exercise 2 here. And for exercise 2 here we have use the generators and relations for d sub 2n, which is generated by rs such that rn is equal to s squared, which is equal to 1, and RS is equal to SR to the negative 1 to show that if X is any element of the dihedral group of D sub 2n, which is not a power of R, then Rx is equal to XR to the negative 1. So intuitively speaking, every non-rotation in D sub 2n is a reflection of the form SR to the K. The braid relation, Rs is equal to SR to the negative 1, lets us move R past S at the expense of inverting the R power, which exactly yields the identity R open parentheses SR to the K close parentheses, which is equal to open parentheses SR to the K close parentheses R negative 1. So let's check this and then get into proving that more rigorously. So for the proof, first we have the normal form. So let's see. So each element of D sub 2n is either a rotation to R to the L, R to the L, or a reflection of the form SR to the K. Hence, if X is not a power of R, we may write X is equal to SR to the K for K integer. That is for some arbitrary integer K. So we'll have that. Now let's move on to step 2. So this we'll look at push R past S using Rs, which is equal to SR negative 1 to the negative 1. So compute Rx, which is equal to R to the R open parentheses S R to the K close parentheses, which is equal to open parentheses Rs close parentheses R to the K, which is equal to open parentheses SR to the negative 1 close parentheses R to the K, which is equal to SR to the K minus 1. So on the other side, right, so we have Rx here. Now we want to look at xr to the negative 1, see if those match up. Open parentheses, sr to the k, close parentheses, r to the negative 1 is equal to sr to the k minus 1. And those are equal. Rx is equal to xr to the negative 1. So what can we say? Well, therefore, for any non-rotation x within d sub 2n, we have r x is equal to x r to the negative 1 as claimed. All right, let's move on to exercise 3. I must have miswrote it in my notes. Let's move on to exercise 3 here. So for exercise 3, we have that if n is equal to 2k is even, and n is greater than or equal to 4, show that z is equal to rk is an element of order 2 which commutes with all elements of d sub 2n. Now, we want to show also that z is the only non-identity element of d sub 2n, which commutes with all elements of d sub 2n. So, intuitively, looking at exercise 33 and 1.1, when the order of r is equal to n, which is equal to 2k, we have that r to the k is equal to r to the negative k. So r to the k is an involution. Then r to the k clearly commutes with all rotations, right? So and r to the k times s is equal to s to the r times negative k, which is equal to s to the r, well, is equal to s times r to the k. Shows it commutes with x. A reflection cannot be central. It fails to commute with r, and a central rotation must satisfy r to the t, which is equal to r to the negative t, forcing t to either equal 0 or t to equal k. So let's look at that a bit more rigorously with the proof. So for step 1, z equals r to the k has order 2. That's what we want to look at. Determine if that's the case. Since r to the n equals 1 with n equal to 2k, we have z squared is equal to r to the 2k, which is equal to 1. Now, by exercise 33 and 1.1, which represents the even case, we have that rk is equal to r to the negative k. Let's see what exactly was at about yes, so part 2 of the exercise has proved that if n is equal to 2k and 1 is less than or equal to I, which is less than n, then x to the I is equal to x to the negative I, if and only if I is equal to k. That's what we have, and that's what we can use right here, which represents the even case. We can say that r to the k is equal to r to the negative k. Whoops. If it's even, yeah, has order 2. So let's move on to step 2 to look at this. With a bitter marker. Step 2, we want to see z commutes with every element. So every element is r to the L or s times r to the L. For rotations, we have z times r to the L is equal to r to the k plus L, which is equal to r to the L plus k, which is equal to r to the L z. So that commutes for rotations. How about for S? Using should be like flips and stuff like that. So using r to the m times s, which is equal to which is equal to s to the r to the negative m, and r to the k is equal to r to the negative k, we have that z s is equal to r to the k times s, which is equal to s times r to the negative k, which is equal to s to the s times r to the k, which is equal to s to the z. So it commutes for s. Hence, therefore, z commutes with r to the L and s times r to the L for all L. Which I suppose L would be an integer, right? So now let's go on to step 3 after I check this. Looks fine, so check step 3. So that's what we want to look at, that no reflection is central when n is greater than or equal to 4. So we showed that z is equal to rk is an element of order 2 in step 1, which commutes with all elements of d sub 2n, which is step 2. Now we want to show that z is the only non-identity element d sub 2m, which commutes with all elements of, so that's really a two-parter. So we want to show it's a non-identity, and we also want to show that it commutes with all elements of d sub 2n. So our reflection is central when n is greater than or equal to 4. So let's let x equal s to the rt, then r x is equal to rs r to the t, which is equal to s r to the t minus 1. xr is equal to srt plus 1. So if we would want Rx to equal XR, then we would have SR to the t minus 1 is equal to SR to the t plus 1. And from this we have, well, so r squared is equal to 1. And this contradicts with the idea that n is greater than or equal to 4, right? So no reflection commutes with all elements. Z is an interesting case then, right? So let's get a closer look at that. So we want to see if the only central rotations are 1 and r to the k. If r to the t is central, then r to the t times s is equal to s times r to the t. So s to the r negative t is equal to s to the r t, and so r to the 2t is equal to 1. With n is equal to 2k, by exercise 33 in 1.1, we have that it yields t is equal to 0 or t is equal to k mod n. So the only non-identity central rotation is r to the k, which, as we know, is equal to z, which, as we've assumed, is equal to z. So combining steps 3 through 4, the only non-identity element commuting with all of d sub 2n is z, which is equal to r to the k. let's move on to exercise 4. Assuming the numbering isn't messed up by my write-up. We'll see. If it is, I'll note it in the description or something like that. Okay. So exercise 4 says that if n is odd and n is greater than or equal to 3, show that the identity is the only element. Oops, that's weird. It's the only element of d sub 2n which commutes with all elements of d sub 2n. So intuitively speaking, by the odd case of exercise 33 in 1.1, no trivial power r to the t equals its inverse when the order of r is equal to n, and that is odd. So no non-identity rotation can centralize S. Reflections never commute with r, same calculation as in the exercise earlier, hence only one is central, the identity element. I feel like I skipped something, but I'm checking through my notes. I don't find anything, but let's see. So let's try and look at this more rigorously with a proof. So step 1, no reflection. We want to show no reflection is central. For n greater than or equal to 3. Let's let x is equal to sr to the t, then rx is equal to rs times r to the t, which is equal to sr to the t minus 1. And what do we have for xr? That's equal to sr to the t plus 1 if rx is equal to xr, we obtain sr to the t minus 1 is equal to sr to the t plus 1. So r squared is equal to 1. This means that the order of that is 2, which contradicts n is greater than or equal to 3. So no reflection commutes with all elements. right. Okay. Now on to step 2. We want to look and see that if the only central rotation is 1. So let r to the t commute with s. From r to the t times s is equal to s times r to the t, and r times s is equal to s times r to the negative 1, we get s times r to the negative t is equal to s times r to the t, which implies r to the 2t is equal to 1. Right, so, oops. It's supposed to be a t, right? Since the order of r is equal to n is odd, by exercise 33, in which we proved the odd case there, 1.1, we have n divides t, so r to the t is equal to 1. So no non-identity rotation centralizes d sub 2n. So it's like, for both of these proofs, even an odd case, you'd say, okay, we can't, let's see if anything commutes with everything here, such that n is greater than or equal to 3. You find, okay, nope, it can't, and then you're like, okay, let's see what the identity can do. The identity can actually do something, and then you're able to say, like, no identity rotation centralizes d sub 2n. Because of that, like that previous case, we can also say in this case, the center, well, not exactly, the center of d sub 2n with n odd and n greater than or equal to 3 is singleton set containing 1. It's the identity. Let's go on to exercise 5. So for exercise 5 here, let x and y be elements of order 2 in a group G. We want to prove that if t is equal to xy, then t times x is equal to x times t to the negative 1. So if n is equal to the order of xy, which is less than infinity, then x and t satisfy the same relations in G as S and R do in D sub 2n. Intuitively, because x squared is equal to y squared, which is equal to 1, we have x is equal to x to the negative 1, and y is equal to y to the negative 1. Setting t is equal to x, y, the product t to the negative 1 is equal to y to the negative 1 times x to the negative 1, which is equal to y times x, reverses the factors. A short shuffle shows tx is equal to xyx, which is equal to x times t to the negative 1. So let me check this, and then we'll look at that more rigorously. So, okay. So for step 1, let's just compute t to the negative 1 with t equal to xy and x squared equal to y squared equal to 1. What we get out of this is that t to the negative 1 is equal to, open parentheses, xy close parentheses to the negative 1. It's equal to y to the negative 1 times x to the negative 1, which is equal to y times x in this case. Now, let's try and derive tx is equal to x times t to the negative 1. So, to derive tx is equal to x times t to the negative 1. Using x is equal to x to the negative 1 and y is equal to y to the negative 1. Let's have tx is equal to xyx. We have tx is equal to xyx, which is equal to x times y to the negative 1 times x to the negative 1, which is equal to x, open parentheses, xy, close parentheses to the negative 1, which is equal to x t to the negative 1. So, tx is equal to xt to the negative 1. Now let's see about reflections. Well, relations here. Dihedral relations with a finite order case. Finite order case. If n is equal to the order of t, which is equal to the order of xy, which is less than infinity, then x squared is equal to 1. Tn is equal to 1. And via step 2, xt is equal to t to the negative 1 times x, which implies tx is equal to xt negative to the negative 1. Let's see the order of x, y's. Then squared step 2. Does that hold? Yep. Okay. Should hold. These are 1s, by the way. This is 1. So is this. This is 2 because of involution. So thus, therefore, x and t satisfy the relations of the standard generators standard S and R of d sub 2n. Proves the claim. X and y be elements, x times t. Do we prove that if t is equal to x, y, this is the case? Yes, we went through all of the different steps, and this is where we got. So that's it for that. Let's move on to the next exercise after I check this. So for exercise 6, we're asked, we're told to show that group generated by A or B such that A squared is equal to B squared, which is equal to open parentheses AB, close parentheses N, which is equal to 1, gives a presentation for d sub 2n in terms of the two generators A is equal to S and B is equal to SR of order 2. I want to show that this gives a presentation for d sub 2n in terms of two generators of order 2 computed in the exercise which we would have looked at previously. Show that the relations for R and S follow from the relations for A and B. And conversely, the relations for A and B follow from those for R and S. So intuitively, what would you do here? Well, take A is equal to S and B is equal to SR. Then AB is equal to S times open parentheses SR close parentheses, which is equal to R. So open parentheses AB close parentheses to the n is equal to R to the n, which is equal to 1, and B squared is equal to open parentheses SR close parentheses squared, which is equal to 1. Conversely, starting with A squared is equal to B squared, which is equal to 1, and open parentheses AB close parentheses to the n is equal to 1. Set S is equal to A and R is equal to AB. Then B is equal to SR, and RS is equal to SR to the negative 1 follows from B squared is equal to 1. So let's look at that more rigorously here in a moment. So with the proof, let's break it down into steps. There we go. Step 1. So from this generator here, AB such that A squared is equal to B squared is equal to open parentheses AB close parentheses to the n, which is equal to 1. Got to 1. Gotta figure out a way to make that not look like 2 sometime down the road. Got to derive the dihedral relations. Right? That's what we've been asked to do, told to do. So assume A squared is equal to B squared is equal to 1, which is what we're supposed to assume, and open parentheses AB close parentheses to the n is equal to 1. So let's define S is equal to A, R equal to AB. Then R to the n is equal to open parentheses AB close parentheses to the n, which is equal to 1. We also have S squared is equal to A squared, which is equal to 1. Also, B is equal to A to the negative 1 times open parentheses AB close parentheses, which is equal to SR. And this is since A is equal to its inverse in this case. So now let's continue over here. Using B squared is equal to 1. Look at 1 as equal to B squared, which is equal to open parentheses SR close parentheses open parentheses SR close parentheses, which is equal to S open parentheses RS close parentheses R. left multiply by S and right multiply by r to the negative 1 to obtain Rs is equal to SR to the negative 1. So therefore Rs satisfy R n is equal, R to the n is equal to 1. S squared is equal to 1. And Rs is equal to SR to the negative 1. That is the defining relations rotation and flip of d sub 2n. Let's think about this. E squared s multiplied by s. Yeah, it holds. Because from here, you know, left multiplied by s over here, get s right multiplied by r to the negative 1. You get r to the negative 1, so really these two should be swapped around, but that's fine. You get rs is equal to sr to the negative 1, which goes on to show that part. So as far as I'm concerned, that part is relatively done, but we still have a whole other part to go. And that is to show order 2, well, from the dihedral relations, to recover that a squared is equal to b squared is equal to, open parentheses, ab, close parentheses, to the n is equal to 1. To show that to be the case here, well, it's a sort of like an if and only if case, right? So we proved that one way, we assume that we have this group that operates on this a squared is equal to b squared is equal to a open parentheses ab, close parentheses, to the n is equal to 1. And then from that we got the dihedral relations. Now can we say that with the dihedral relations that we can get back to that equation, that function there? Equation. Yeah. Let's see. So let's start with step 2. So from the dihedral relations, we want to recover a squared is equal to b squared is equal to close parentheses ab close, open parentheses ab close parentheses. The n is equal to 1. So let's conversely assume d sub 2n equal to the dihedral group, which is generated by rotations rs such that r to the n is equal to s squared, which is equal to 1, and rs is equal to s r to the negative 1, and set a as being equal to s and b as being equal to sr. Then a squared is equal to is equal to s squared, which is equal to 1. B squared is equal to open parentheses sr close parentheses open parentheses sr close parentheses is equal to s open parentheses rs close parentheses r, which is equal to s open parentheses sr to the negative 1 close parentheses r, which is equal to s squared r to the negative 1 times r, which is equal to 1. Moreover, AB is equal to S open parentheses SR close parentheses, which is equal to S squared times R, which is equal to R. And that implies that that open parentheses AB close parentheses to the n is equal to R to the n, which is equal to 1. 1. So AB satisfy a squared is equal to b squared is equal to open parentheses AB close parentheses to the n, which is equal to 1. From that, we have shown, therefore, that the two presentations are, in fact, equivalent. Group generated by AB such that a squared is equal to b squared is equal to open parentheses AB close parentheses to the n is equal to 1. That's the same thing as the dihedral group, d sub 2n. So that's it for exercise 6. Let's move on to exercise 7. So we have to find the order of the cyclic group, the cyclic subgroup, sorry, of d sub 2n generated by R. So how would we do this? Well, intuitively, in d sub 2n generated by the set generated by r or s, such that r to the n is equal to s to the s squared, which is equal to 1, or rs is equal to sr to the negative 1. R is a rotation by 2 pi over n. The subgroup generated by R consists of all rotations by integer multiples of 2 pi over n, namely 1, r, on and on and on until we get to r to the n minus 1, n distinct elements. So let's try and get into this a bit more rigorously here in a moment. So for step 1, let's try and describe a subgroup generated by R. Rotations. Let G be such a group. Well, let R be generated by, let G be generated by R. Then every element of G is r to the k for some k in the integers, so some integer. Okay. Step 2, geometric representation. Interpretation. Representation is a specific thing. Interpretation. So, if k is greater than 0, r to the k is rotation by 2k pi over n. If k is less than 0, r to the k is rotation by -2 times open parentheses, -k close parentheses times k over n. So let's try and reduce this. Reduce exponents modulo n. If the order of k is greater than or equal to n, the rotation r to the k equals r to the l for some r to the l for some 0 less than or equal to l less than n, same angle modulo 2 pi. So G is equal to the set containing 1 r squared all the way up to r to the n minus 1. try and count these. Well, let's see what I mean. So the rotations one r to r to the n minus 1 are distinct. That's the nature. So the order of G is equal to n. So therefore, cyclic subgroup generated by rotations generated by R has order n. I think there's like, we could go back and prove that they are actually distinct again through minimality, right? But I mean, we've already kind of proven that, so they're distinct. The order of G is equal to n. Ergo, the cyclic subgroup in this case is also equal to n with what we've already established before. Let's go back and look at that. Yeah. Okay. And if I'm wrong, just correct me and I'll go back and fix it. So, we've got time. Do we have time for? Let's go ahead and solve this one, right? Exercise 8. So exercise 8 has, well, let G be the group of rigid motions in R3 of a tetrahedron. Show that the order of G is equal to 12. So intuitively, you'd label the four vertices. A rotation is determined by where it sends an ordered adjacent pair of vertices, so 4 choices for the first vertex's image, then 3 choices for the second adjacent to the first. Remaining vertices follow uniquely from that. So let's try and look at that a bit more rigorously. So, for the proof, step 1, fix the image of one vertex, So we're going to label the vertices one, 2, 3, 4. The rotation rotation sends vertex 1 to any of the 4 vertices. 4 choices. So let's look at what happens when we fix the image of an adjacent vertex. Fix the image of an adjacent vertex. So each vertex of a tetrahedron is adjacent to the other 3. Once the image of one is chosen, the image of 2 must be one of the 3 vertices adjacent to the image of 1. 3 choices, right? Only 3 places to go. With the images of 1 and 2 fixed, the positions of the remaining 2 vertices are forced, hence rigid motion. So the number of rotations is 4 times 3, which is equal to 12. Therefore, the order of G is equal to 12. QED.